on iterated hash function, if you remember. And in terms of hash function, again, just to recollect on what we were actually doing, we have a message and we want to make it integrated, like the integration and the integrity of it is maintained and the authentication is maintained. For that purpose, what we are doing, we are trying to encapsulate the message using some form of a hash function, and that hash function will generate some kind of a message digest, and that message digest will be of different set of bits, and that message digest is supposed to be transmitted over the air, right? So that is what the process is. What iterated hash function is an indication where we are making sure that the process to develop that function is to be discussed. And in that, the fundamental block structure based on which all the algorithms are working, guys, please concentrate. Where the first thing that we discussed was the Merkle-Demark scheme, in which the primary objective is that we have to have an original message of certain number of bits, and that needs to be divided into different blocks, and that block will actually be considered either as a plain text or as in terms of key, and definitely there will be a ciphertext that will be generated with the help of an initial H0, which will be considered as the initial hash function, alright, or the first value, that H0 in the left hand side. But based on that, we will go on changing the different configuration, like for example over here, the plain text, the key and the ciphertext is the position of this scheme. Similarly here we have a different scheme. Mostly the configuration is the same, except that there is a zoring that we are doing extra. And then we found out that there is another way of doing it, which is the dual of it, where we are changing we are using the original message block as the key, and or rather the plain text, and based on that the key is used as the H0 or the message hash function. But the most important and the interesting part was when we discussed about the MD4, which I told you is the basis of our discussion of all this iterated function. Based on this MD4, we actually will discuss the SHA-512, which happens to be a very, not a complex, I would say, but kind of safe iterated hash function until a certain period. After Whirlpool was another algorithm which was developed in a much later stage of around 2007-8. So people started to believe that SHA will have certain issues, and hence it got obsoleted for that matter. So today's discussion, we are going to start with SHA-512. But before going to that, let me just show you that process that were involved, just to give you an insight on what we have done on last day's class. I can't repeat that, but I'll just show you this diagram which I already have uploaded, but it will not be there in your books and all. It will be there only in the course page. It's the interpretation of MD4. Although you will find that this MD4, the structure of it starts with a 512 set of blocks, and there are empty such blocks. So this is, we already discussed in PPT, this is just a representation of it. And this 512 blocks will be, if I consider any one of this block, that will be repeated 3 times. So this is the 3 times which is getting repeated. And the repetition is done 3 times because there are supposed to be 3 sets of round. Each of the round will have 16 states. That means total 48 such states it will go through. And that were given by R1, R2 and R3. So R1, R2, R3 indicates the 3 different rounds. For each of these 3 different rounds, there are 16 states. If you observe over here, this S0 to S15. So these are my 16 states which we are looking at. And also you will observe that for this individual round, as I already had told you last day itself, we will actually come across a scenario like this, where for this ABCD, suppose this is my initialization of the H0. So for all of these 4 ABCD, there will be a configuration of this nature, the one that is given. So basically there is a XOR operation that we are doing over here. Then the message comes in, and that also is getting XORed. And then there is a third XOR which is coming in with a constant matrix, which is CR. And as I told you that if suppose it is in round 1, that the states that in round 1, they will undergo a function which is if. So this FR is equal to if function. when we are considering round 1. This one. Alright. And the predefined CR for that particular round will be all zeros. Alright. So this is basically for the round 1, the schemes that we are associated with. And similarly, also this SRK that you are looking at, this is basically shifting by right by the number of bits. Alright. So for example, as I told already, so suppose we are at, I think last day I had written it down. So suppose I am at S0 state. Round 1 S0 state. Then it is meaning that we have to shift right the bits by 3 bits. Now when we are at S1 state, suppose, then the rule is we have to shift by 7 bits to the right for the existing bit structure, whatever we are looking at. Similarly, S2 will have 11 set of bits which will be right shifted, and finally S3 will have 19 such bits should be right shifted, and this will go on until we are reaching up to S15. This is for one round. Similarly, when we are in round 2, we are going to have a function which is merge, and for that the CR function will also be a constant which is already predefined, and similarly the shifting operation will be 3, 5, 9, 13. All these are standard because it's an algorithm which has been defined by someone. So these assumptions are made based on certain process and properties which we cannot change at this point of time. So these are the standard techniques which we have to follow. So for each and every round, we will go under certain degrees of function. We have to check the function. Which function? This function, FR, which depends on BCD. So this BCD is basically my X, Y, and Z, and these functions have been defined over here. Please look at this document carefully. All the detail is there in the PPT slides as well. But this is, I feel it's a more consolidated diagram for that matter to understand. Because books might not give you it might confuse you a bit with the material that is there. Alright, so these functions are, so this X, Y, and Z are basically B, C, and D. So each and every time the BCD will go through this particular function based on which round we are in. The output of it will be XORed with the A. That output will come and be XORed with the corresponding MK, which is the bits. What is MK? If you remember that this is what the MKs are. MK means M0, 1, 2, 3, whatever it is. So that is getting XORed. And after that, the CR will come in. So whichever round we are in, that particular CR will again get XORed. And finally, whatever the output we are getting, that is getting shifted over here. Alright, so this is getting the shifted, and that too shifting with particular order of shifting. And finally, here there is a shifting of the links that we are looking at. Problem with that, the peaks which were there, this thing over here, it is now C. C has become P, P has become K. So like that, ABCD will have a switchover of the elements that is present. So now this ABCD, the one that is generated over here, A prime, B prime, C prime, D prime, this might be somewhere here. So that A prime, B prime, C prime, D prime will be the input to the next rounds. Which will it be? This one. Again, the same process will go, but as it is in round 2, so this function will be next function. And it will continue. So this is the process which was adopted for MD4, and it worked pretty well up to a certain extent. But naturally, as MD5 came in, where we actually added another binary function to it, the version got changed. But as I said, the SHA-512, when it was introduced, it was much comprehensive compared to MD4 and MD5. Alright, so let's see with our discussion on SH4 and how it is done. Please. Yeah, please. This one. This is all right shift. So all right shift. This is SRK means the state, and K is the, like S0, R is the round. S1, K state. We will have to shift by right. Left shift, did I tell you? Also, let me show. Let me just check it. Let me just check it. Yeah, left shift. Sorry. It will be a left shift. Sorry. So, okay, so the shifting operation will be a left shift operation of the number of bits which you are looking at, 3, 7, 9, whatever it is, for that particular round. Alright. So this is what we had discussed about the and this function is nothing but the three sets of XOR that we are already have discussed. So this is one XOR, this is one XOR, this is one XOR. So that's what is happening over here, right? So now let's discuss. So this all the details are there in the PPT. So please go through this. This all see over here 3, 7, 11, 19. That is only what I have written in that handout. Okay. So the same thing. Now let's discuss about the MD5. Just one part of it. So you can observe that this is the only element that we are looking at, a function over here that has been added. All right. So that is the only change that we come across with the MD5 algorithm, but we don't need that for that matter. What we require is the secure hash algorithm. Please focus on this carefully. Now this SHA, one of the biggest improvement from the other one is that we have the 512 bit of message digest. Unlike to the MD4 where we had 128 bit, there is a significant improvement in the number of message digest. And the reason is that if you go on increasing the number of bits, naturally the possible combinations will be more. So hence the redundancy will be reduced. So in that way, this is becoming more secure. So that's one of the reasons. Now let's see about the compression function. Remember, we are trying to find out the way the hash functions, the digest will be generated. Alright. Alright, so this is about the SH-512 that we are considering. So if you observe, the process is almost the same as we have discussed already. So now, instead of 512 bits, we will have 1024 bits. Alright, so we will have 1024 bits over here. And we will consider the initial value as 512 because we will want to have the digest of 512 bits. So the initial message digest will always be of 512 bits. And we are sending that over here in this compression function. We'll see the compression function later. We'll see that separately. But if we try to focus on this first part, you can observe that this should be a multiple of 1024 bits. It means it's the same concept that we discussed about in MD4, that whatever happens, that the block set should be of 512 bits. Here, same way, padding needs to be added in order to make it 1024. Alright, so now let's see about this padding part first, and then we'll see the compression function. So let's see about this. Let's skip a bit. This is one of the diagrams that I want all of you to focus on. Alright, so if you observe here, first of all, the original message comes in. I'll give you an example after this also, because it's a little difficult to perceive as such without giving the example. So what we are going to do is we will have an original message. We will always pad by a certain variable. You can see the length is variable. Why variable? Because your original message can be of any dimension. It can be of small, like for example, 24 bit. It can be 100 bit for that matter. But we have to make sure that whatever happens, it should come to 1024 or its multiple. Otherwise, the block sets won't happen. You see over here, the block diagram. These all are 1024 bits. So this block won't happen if the total bits over here is not a multiple of 1024. So the purpose of that is we are trying to add the number of pads such that eventually the final message is of 1024 or greater multiple of it. It can be 3 times to 1024. That's fine. In that case, we'll have 3 blocks. But it should be multiple of 1024. Okay. So that keeping in mind, we are discussing this. So you can see length will be variable naturally, whatever we require. And then finally, the configuration is that at the end, we are going to append the 128 bit of the original message. Whatever be the original message, we are going to convert that into 128 bit and we are going to append. So in a message, the original message of 1024, we will have a portion of the original message, whatever be the original message, like 20 bits, 24 bits, 50 bits, 100 bits, whatever it is, that is here. Then the length of the variable which will be of certain duration, which has a calculation of it, I'll tell you. And after that, the length of 128 bit, it means the original message will be converted to a 128 bit message, and that 128 bit the configuration will be added to it. Unlike to MD4, you can see this is the MD4 diagram. In that also, we also had the similar thing, except that we had a 64-bit over here. So that is why MD4 is important, because all these configurations are like linked up one to another. Alright. Now let's see with an example on how this is to be done. Okay. This example is very crucial. Please focus on it. Now suppose the example is that you have the original message as ABC. People at the back, if you are not listening to it, it's okay. But if question comes in and you are not able to solve it, I don't tell me, sir, please consider for passing me for this question. Please concentrate on this. So you have the original message as ABC, right? Now, if you convert this ABC, focus on it. So what is the, you just keep a mind of it, original message, then we have a padding, then we have the 128-bit of the original message configuration. That's the configuration. So first what we have to do is, we have to convert this any message into binary. So you can see that ABC has been made of this nature, and that total length is only 24 bits. But we know we have to make it 1024 or its multiple. Right? So what we have to do is, first of all, we have to make an arrangement of this nature. Please make a note of this. Message length should be congruent to 896 mod of 1024. Please make a note of it. This part. So whatever happens, your message length means original message plus the padding I'm talking about. Because that last 128 bit is fixed. Whatever happens, you have to keep that 128 bit. Say, leave out that. So the thing is, you can see this, can you add up this one, 896 plus 128. What is the value? Exactly. So 1024 comes in over here. That is why this is kept as 896. Can you understand what I mean? Total message is 124, out of which 128 is definitely will be there. So the rest 896 should be the portion of original message plus padding. So that is what is mentioned over here. So that's why the message length is congruent to the message length. Message length means the original plus the padding should be congruent to 896 of mod of 1024. Because mod of 1024, that's a maximum. Now if you observe over here, that is what I have mentioned over here with respect to the bit configuration. If you check here, the 616268, this one, this is the 24 element of the nature of it. You just convert this, you will get this part. The rest are all zeros. Rest are all zeros to make it 128 bit less than that of 1024. Now the point is, why I'm making is that you can see the rest of the zero that you are looking at. Okay, so we are filling up the rest of the elements with zeros, and that is what we are calling as the padding. Alright, just to make it 1024, otherwise the blocks won't happen. So, keeping that in mind, you can see over here, now what we have to do is, the original message needs to be converted to 128 bit and needs to be appended at the end. So that is being converted. See, 24 bits in hexadecimal is 18. That is converted to a 128 bit configuration, and that is looking at something like this. So this portion that you are looking at, this is my 128 bit that has been added. So now with the 24 bit which was there, original 24 which was there, along with that we have padded the rest of the bits using the formula, whatever is left out, that padding plus we have to do the 128 bit of the original message in hexadecimal format, and that being added. So now if you observe this whole thing which you are looking at, that will be of 1024 or its multiple. Right? So that is how the padding plays an important role. Both in MD4 it was also there. In MD4 also was there, but since MD4 is not there as much in our syllabus, I thought of giving this example over here in SH4, which is a more realistic configuration for that matter. Please.
First one then
Yes, we have to put a 1, and we have to, padding has a property. I'll tell you that after this example also. Padding has a particular property. In MD4 also I told you that it has, it's very easy actually. The first bit should be 1 and the rest will be all zeros. So suppose for example you have 100 padding bits. Just example. You have 100 padding bits. So in that case, your first bit should be 1 and 99 zeros will be added. So that will be the padding. Simple as that.
This now.
In this example, you check here 24. Can you find a 24? How many number of bits you require for a padding? Can you do that? Acha. For that to do, let me just give you this example and maybe you can able to understand. Suppose this is the example. I'll come back to this example once again. Can you see this example for that matter? You have 2590 bits as the original message. Just like we had 24, we had 2590 as original message. The question is, how do I find out the number of padding bits which are required? Alright. So for that, you have to just do the same thing. You can see 2590, basically the message plus padding is the original message, remember. Alright. So that is what it's doing. We are taking everything in a minus here. So minus what? So it is something like M plus P plus 128. This will be the original message, total message. Alright, so that's why you can see there is a minus sign over here, minus sign over here. So the point is you are getting a minus 2718. This one. We are trying to calculate what is my padding. Message is 2590. So in this case, in the right hand side, so minus. Your 128 comes this side, so that's again a minus. So that's why 2590 and 128 is having this minus sign. The point is here you have a negative sign. Most of the time, what we have done, we don't consider negative. We usually take the subtraction from the maximum value. That's how we have solved it, right? But in this particular configuration, the generic rule is, because here it is 1024, you please note down this formula. So it is just like k minus n mod k, where your n is, for your k is 1024 and your n is 2718 without the sign. So please make a note of this. K minus in bracket n mod k, where my k is the mod value and n is the unsigned value of whatever is there as a coefficient, 2718. And if you substitute over here, you will get 354. You will get 354 as the value of padding. Can you understand this? What I did here, it says k is equal to the mod value. So 1024 minus in bracket 2718 mod of 1024. This is a generic rule. Please make a note of it, because in SHA-512 you don't have anything apart from 1024. So that's the thing. But if it is coming as negative like this, it's really difficult at times. So this is a generic rule that you might follow. So in that case, you will find 354 is the number of bits required for the padding. Now 354 is the padding, as he was rightly pointing out. Padding consists of 1 followed by 353 zeros. Can you understand that? In that same manner, can you do it for the 24 bit, the previous one? So you have 24 bits as the original message. So minus 24 minus 128. That will be the configuration, right? In the previous example. Can you do it quickly and tell me what will be the answer for how many number of paddings you require? So this will be like this, mod of 1024. This is, see, this observe over here. What we have done, what we are maintaining over here, this is my original message. We require, now this is as in our example, the previous example, we had 24 bits. Then we are adding a padding of certain duration, and we are adding a mandatory 128 bits of the original message. So this 3 is actually following the original message of 104 bits. In this particular question, we are asked to find what is my padding now. So what we did, message is 2590 plus 128. So original message is given by 896, that 896 mod of 1024. So we took that in the right hand side. So that became minus 2590 minus 128. Message minus the 128 bit. Mod of 122. Now this is a negative value. So that negative value can be calculated. Usually this is possible. Okay. Usually what we do is, whenever the negative value comes in, if the mod value is greater, We could subtract and we can say that what is the value. Instead of doing that, use this formula for it. Because in this case, the value of k is the odd value, n is this value without any sign. Then there won't be any error in the calculation. So that is what is given here. This three.
Minus sign.
It won't be considered over here. Which minus here? That's what that minus sign is there. No, so I cannot take a mod of the minus sign. I have to remove this. How we are doing it? We are doing using this as. Here k is given by 1024, n is 718, mod of k. And if you take this whole calculation, it will come as 35, which is a positive.
And it's just a positive from outside.
Positive for yes, no answer sign. Like you don't take the sign, negative sign. Can you get me the answer for this? Sorry? 830? 876. 872. So 872 means you have first bit as 1 and the 871 bits will be of 0. That should be the configuration. Alright, so in the diagram, previous diagram, if you observe, I don't think there is a 1. I missed out most probably. So there must be a 1 over here. There must be a 1. So basically the original message of whatever be the length, then we have the padding and then the mandatory representation of the 128 bit of the original message. So this particular example shows that. Anyway, yeah. Just after the first one, like suppose in the over here, what is my message? You tell me, 24, right? Can you see the 6162638? So this is my 6, I think. This is my 1. This is my 6. This is my 2. This is my 6. This is my 3. Right? So that is basically 616263. Now, if it is 1, 1000. So 1000 and the rest is 0. So first, this 1 is this 8. Right? Can you please check this properly? This 8, please look at this last 8 over here. Please focus, Manjan. I know that this might be a little tough at times. That's why I found this example somehow. 616263. This is happens to be the configuration of the 24 bit. Now you check 8. 8 is 1000. So that 1 that you are looking at within that 000, that 1 is the starting bit for the padding. And the rest zeros, if you go on counting, you will find that that will be total number is 871. This total number of zeros up to this. So 100 will have 3 and then rest 0 starting from here to here, it should count to 871. And after that, we are doing that 128 bit implementation of the original message. Clear with the example? Right? So that's how we are going to pad the message of any length and we will make it to 1024 or more. Let's take another example. Let's make sure we can understand this carefully. See this example. Input message is of 2348. Same example, it's simple because these methods are all the same. If you understand one, you will do it also. Now the message length, if you observe, so we have total of 300 only. What we have to do? We have to make it around 1024. So 1024, remember we have to make it 896 to be honest. Somehow we have to make it 896. See here. Because by default 128 bit is allotted for the original message, the padding, the length version, 128 bit. So the configuration indicate we require a 596 odd padding. This is my original message plus padding, that will be 896. 896 plus, when we look at 128, that will be 1024. So let's see, you can see what we have done. 2348 bits plus 596 odd padding should be congruent to 896. Okay? And then, so that means 2348, the original message, the earlier one, plus 596 padding, so 2944, plus 128 bits, because this is the message length. By default, it is coming. So it is 3072 total number of bits. 3072, if you keep it till 2944, it is not a multiple of 1024. So this 128 bit, if it gets added, which is supposed to be, the final answer is coming 3072, which is divisible by 1024 into 3 blocks. So whatever be the number of, is like, for example, we started with 24 bits. Here it is 2348 bits, whatever it is, make sure that that is congruent to 896 mod of 1024. We find out the remaining bits, we add that remaining bits to the original message, and that will be the original message plus padding. Then we add the 128 bit on top of it to make it 12024 or multiple of it. Alright. Other than this multiple, SHA-512, and even in Whirlpool, you will observe it won't work. That's why it is a configuration that we have to follow. So this is about the padding part. Alright. So this is only the first part of it. You can observe over here, if I go back to the block diagram once again. So this is about the 1024 bit blocks. How these are being considered from the augmented message. So this augmented message contains original message, padding, and the length variable of 120. So that makes it 1024 and multiple of 1024. That's what we have discussed. Yeah. Now we come to the compression function over here. So let's see. This is also a bit simple, but there's a process involved. First of all, the thing is, we will represent this 1024 bits into 16 words. Okay, that's where it starts. So 1024 bits will be configured or understood as 16 words. And another thing, the message digest which will be generated will have 8 words. So these are the two specifications only. First specification is the 1024 is kind of broken down into blocks. Instead of blocks, they consider it to be words. It's just a nomenclature, nothing else. It's the same as a block. So 16 words, each of 64 bits to make it 1024. So total is 16 words. This is for the message I'm talking about. Message block. And the output, the message digest which will be generated, it will be represented in a form of 8 words of 64 bits. And that means 512 bits. Remember in SH12, 512, the name is itself SHA-512. 512 indicates the message digest length of 512. That's why don't ever forget about this value. And if you know 512 and if you know 8, you will know that 64 bits is to be used. Alright, so it's in a way it's calculating very easily. Now let's see the block diagram. Okay, how it is working. Now I'll go one by one to explain what exactly is happening. Don't look at this right hand side of it. For the time being, don't look at the right hand side. You focus on this area. Alright. So if you observe what is happening, we have block of 16 words which we have defined. So 0 to 15 are the original words. But as per the algorithm, we will require 80 such words. 80 words we will require. Very similar to what we have done in DES and AES, in fact, where we had a simpler process of key expansion strategy. Very similar. So here, if you observe, this is my 15. Green color means this has already been defined. Already there with us. But if you observe here, the last word over here is W79. So that means it starts from 0 and it goes to 79. It means you will finally require 80 such words. So this side of the story, this one that I have not, like I have just marked as like this is the part which is called as the key expansion strategy. Just like we had it in AES, we had a key expansion strategy. Same way we have the right hand side, which is nothing but the key expansion. Okay. So what we are trying to do, we have the 16 words. We are going to use those 16 words. Along with that, taking help of those 16 words, we are going to formulate the next 16, and all. That's all it is. But to generate that, naturally, if you remember in AES also, we actually had some formulas. Rot word plus subword, like that we had generated, right? Same way we are generating over here. So please make a note of this element. If you observe WI, I think I have a separate document for that. I'll just show you that. 1 minute. Yeah, I'll show you that over here, which is comparatively easier for me to understand. So you see over here, the same diagram has been shown. And if you see WI, please make a note of this. WI, which is over here, any word after that 16th word will be given by WI minus 16. I can't help it, but this is just an algorithm. So please make a note of the equations. WI minus 16 rot of WI minus 15 plus, rather XOR in that way, WI minus 7 and rot of WI minus 2. Please make a note of this equations. This is very much evident from here itself. You can see WI 16, I minus 16 is over here. I minus 15 is over here, which goes to some kind of a rot operation. And WI minus 7 comes straight over here. WI minus 2 comes in through something called as a rot function to this. And finally, we are giving a XOR over here. So all this is getting XORed and we are generating WIs. This is the key expansion formula. Just like we had it for AES, this is just a different case. And to make it even more complex for you, what I can feel from the faces, this rot function is generated by something like this. See for yourself. See for yourself. Rot time shift by L bits. Can you see here? Rot shift 1, 8, 7. It's mentioned over there. I don't know whether you are able to see it. Here it's mentioned rot of 1, 8, 7 or 1-8, 7. That is mentioned over there. I don't know whether you are able to visualize it. So that means this rot function is not only a rot function. It's a rot shift function, ideally. And in that, what I mean is, first element over here, the first entry, rot shift by L element. So this is my first entry. Are you with me in this? Can you able to understand what I mean? Rot shift is the function. Same as I've mentioned over here as rot. Just to make it a little less complex for that matter. So rot function is given as this rot shift L-M-N, where L indicates rot right shift by L bits, XOR rot right by M bits, XOR shift left by N bits. That means whenever this WI minus 15 bit comes in, which is a 64-bit configuration, from that 64 configuration, first bit you rotate by right. 8-bit, M bit, you rotate by right once again, after the operation is done. Last one, shift left by N bits. So that whole configuration is what is being fed over here. Shifting is different, rotation is different. Shifting is, you are shifting from shift left by, you are saying shift, and rotation in that way is correct. This is left shifted. One is left shift, the last operation, but see the hierarchy. Rotation, then left shift. Rotation by right, then left shift. Yes, please. See, X means what? X is here W5, W5, because X is here. This is my argument over here. So WI minus 15, whatever be the 64-bit configuration it has, shift left of that bit by I bits. Padding left bit by zeros. Okay, it's mentioned in that way. So then though it's mentioned there properly. I mistook it. So the shift left, please observe this. This is rotation part. It's mentioned over here. The rotation, the two rotations are the proper rotation that we are looking at. Left one, the shift rotation, is basically we are left shifting and the rest we are padding by zeros. So for example, suppose we are looking at W16, word number 60, somewhere over here. Suppose this is my W60 somewhere over here. So that will have Wi minus 16. So I is over here is 60. So 60 minus 16, W44. So whatever be the configuration of the 44 bits, that comes directly. XOR with rot shift of 187, which is same for any round, of W45. Why? Because this is I minus 15. I is my 60. 60 minus 15 is 45. So that becomes W45. Rot shift is again same thing here. So here rot shift by 1 bit, like rotate by 1 bit, then rotate by 8 bit, and we have the shifting of 7 bit. Same way W53 is directly coming because I minus 7 directly comes in here. So that's why 53 and rot shift of the last one. So this output will be W60, the word 60. Like that, W79 will also be generated by this key expansion process. Can you give me for W4, W16 for that matter, what will be the configuration? W16, if suppose I have I equals to 16, what will be the function? I'm talking about this one, W16. So based on the formula, can you tell me what will be the W16 will be equal to W0, yes, XOR of rot shift 187, W of 16 minus 15, that means 1, so W1, XOR W 16 minus 7, that is 9, W9, XOR rot shift 1961 6, W of 14. So if you observe for W16, we are using the element W0, W2, W9 and W14, which are all available with us. Because initially that 15 or 16 data is already present with us.
So, this 1879 flag will be for
Constant, that is fixed, yeah, that is fixed. Okay, so this is about the key expansion. So basically what we are trying to do, for each and every block of 1024, we are breaking it down in a way such that we are dividing it into words. Very similar to what we have done for AES. You will find the Whirlpool also will be working in the same manner as terms of words. So now the words are being configured of 16, but for the algorithm to work, we will require 80 words. So from 16 to 80, that generation is done by the process used over here. 2 rotation, 1 shifting operation, and the particular bit configuration. Based on which we will generate this 18. And finally, we will have a block diagram like this. I'll end up the discussion over here. We'll come back next day. But if you observe carefully what we have done, that this is my initial message digest. Now, initial message digest given. Initial message digest of 512 which is given to us. This is the standard. Just recollect what we have done in AES. The initial A0, B0 were given to us. Remember the initial table, rot values for per element was given to us. So here also it is given. So this is my initial values. Now this goes to the rounds. This goes to round up to round 79. That is why you require 80 such words. W89. This is 79. So what we have explained right now is to how to generate this individual word. This is 88th word. So now we are clear about how we are generating this 80 word, why we are generating this 80 word. Because there are 80 such rounds. Just like in AES, how many rounds we had? In AES, 10 rounds we had, right? 10, 14 and all that different. But leave out, at least in general, we had 10 rounds. Same way we will have 80 such rounds. And in each of the rounds, what is going inside this round is a discussion altogether. We'll discuss next day. But basically what is happening, all this initial A0, B0 is fed to this round. W0 is the first 64 bit which is there from the message itself. K0 is generated by the key coming in. That also is a discussion, I'll tell you. Based on that, we will find out that what are the final result coming in over here. This last ABCD that you are looking at over here, this is the values for the next block of the digester. So this is my 512 again. This will be a 512 bit. But in between there are 79 rounds or 80 rounds rather, through which the data will pass. And that is given over this whole section. So let us stop at this point. We come back next day and we'll finish off this part of the round, what goes inside the round. Because this is same as that of, very similar, I won't say same, but very similar to what we have done in AES. Okay, each and every round will have certain like property. For example, I'll just show you that how the each round will look like. This is the each round will look like. So each round will also have certain functions on through which it will pass through, and finally we'll get the result for ABC. Right? So we'll see that. Next day we'll come back and we'll see.